All right. Hi, everyone. Thank you for attending today's webinar on residential testing. This webinar will be recorded, and the recording PDF will be sent out to all attendees. As you see here, we're trying out something new today with some polling. If you wouldn't mind, entering what your background is, that'll help Robbie and I know who's in the room. So Robbie and I are sponsored by the Colorado Energy Office to put on these trainings. We've been working with the Colorado Energy Office to put on this webinar series. And as you can see here, we've got about 9 or 10 more. I do want to point out that on the last one, the date was changed to the 12th instead of the 5th. So just so you all are aware, I'll keep reminding you all. But in addition to these webinar trainings, we also do provide tailored trainings for groups or companies or jurisdictions and technical assistance for code adoption. So if you have any interest in finding out more about that, just shoot me an email and we can touch base. And then in addition to the trainings and technical assistance, we've put together a code adoption toolkit that reviews cost implications of changing code cycles, benefits, a troubleshooting guide covering ICode conflicts, a whole bunch of different resources. We've been working to update that to 2021, so there's a good amount of info on there relating to 2021 in addition to 2018 now, so feel free to check that out. And then throughout the webinar, we do want to encourage questions. Please use the Q&A function if you do have questions, and I'll let our presenter know at the end. And then, as I said, we are going to be using the polling system throughout to try and engage with the audience a bit more. So today's presenter is Robbie Schwartz, and he founded Build Tank to be a practical building think tank to do research, education, and work with builders to ensure that homes are not only built to comply, but also perform. So today, Robbie, it looks like we have 35% of people are building officials. We've got 30% of architects, energy consultants, and contractors. We've got a wide variety of people in the room today. So with that, I'll go ahead and let you kick it off.
Okay, so thanks everyone for joining us today. I'm going to share my screen. And I also am going to turn off my video so you can concentrate on the slides, and I'll come back to you later on today. We'll have a couple more polls as we go as well, go through things today. So our plan today, and thank you, Erica, for a great introduction as well. Our plan today is to talk about diagnostics and the three type of testing that we do. So our first question ultimately is, why do we care about diagnostics? Diagnostics ultimately help to ensure that we achieve the requirements of the code, and the code is asking us to do specific things. Another way to think about it is, how do we achieve this first portion of the intent statement of the code that says that we need to regulate the design and construction of buildings for the effective use and conservation of energy over the useful life of the building. So what this part of the intent statement is really talking about is long-term durability. And the number of the tests that we do deal with long-term durability, primarily with regards to moisture management and how we gain control and predictability in that house from a moisture management perspective there. Also, we need to think about home performance. The code is looking more and more at performance and how things actually work in the code. And performance can be described as the science and practice of building homes according to the comprehensive specifications. And those comprehensive specifications, in this case, really are those things wrapped into the IECC and the IRC, potentially the IBC if you're using that part of the code, and how we ultimately create a house that is safe, comfortable, efficient, and durable in working out there. So this notion of diagnostics and getting what we expect instead of what we inspect sometimes is changing the way that we look at houses as well. So we're looking at houses from more of a performance perspective. So we can't walk in and just say, yep, there's insulation in the wall. We have to look at how that insulation is actually performing as it's been installed to ultimately achieve the type of thermal envelope that the code is asking us to achieve. And the code begins this process of defining the thermal envelope. And it tells us that we need to have a depiction of the thermal envelope in our construction documents. But it goes further in the definition section and defines that thermal envelope as a boundary condition that's separating conditioned space from unconditioned space, and ensuring that we have alignment and continuity of that insulation in there by talking and describing what an air barrier is in that house. So the air barrier is not a single material, it's this combination of materials. It may be a single material, but most often it's this combination of materials inside and outside our house. So our exterior sheathing and our interior drywall, for example, is our primary air barrier systems on the inside and on the outside that is creating that boundary condition that's separating conditioned space from unconditioned space. The code goes even further than that, however, and says that we have to have the continuity of that air barrier system all the way around the house. So in this depiction of the building thermal envelope, we're talking about that green line that's able to go all the way around the house, across the conditioned crawl space, up through the bedrooms and down through the basement, so that we have that continuity and that separation between conditioned space and unconditioned space. So from a applied building science perspective, we're trying to gain control and predictability of airflow, thermal flow, and moisture flow. And this testing that we're doing is trying to ensure that we're meeting the requirements of the code in order to get that control and predictability. So I wanted to ask my first poll question here, Erica, which is basically, what does the IECC currently ask us to test for? So just take a second here to get a few answers in. Okay, what are we starting to see there, Erica?
We've got a few answers for bathroom fan. That one's leading by 67%. I'll give it another couple seconds here, and then I can share the results. All right, I'm going to go ahead and end the poll. Okay, can you see the results, Robbie?
I can see the results now. So bathroom fans got 65% of respondents there, and then the rest were kind of equally looked at there. So what's interesting here is that bathroom fans, up until the 2021, the IECC never asked us to test our bathroom fans. We have a specific ventilation rate that they have to achieve, but we're not required to actually test them. So the three things that the code in the 2021 asks us to test is for air leakage, so how airtight a house is. We have to test for duct leakage, and we have to now test for mechanical ventilation and the two different types of mechanical ventilation that we have to test to. So these are the three tests that we're going to go through today that the code is actually requiring us to do. And remember that the code no longer calls these things mandatory. They just call them requirements, but the reality is that they are mandatory. You have to do that. So the 2021 just kind of changed that language up there. Obviously, they want to keep things as clear as possible there. So they always are changing things. So when we talk about blower door testing and this other testing that we're doing, we're always talking about ultimately how air is moving through our houses and how we can gain control and predictability of that airflow through our houses. So we need to think a little bit about that air movement in our houses. So if you've seen other presentations, we're going to do a little bit of review here. The way I like to think about air movement in our houses is to think about air as a freight train. It's carrying something from point A to point B. And what it's ultimately carrying is heat, moisture, and pollutants through our houses and then potentially from inside to outside our houses. And the problem with that ultimately is that it doesn't have a clear point to deposit its load. So it might deposit its load from inside all the way to the exterior, that ambient air outside, but it also might deposit its load within a building assembly. And that's where we get building durability and other building science issues popping up because we can get repeated wetting when that happens. But for air to move, we basically need two things. We need a hole and we need some type of pressure difference across that hole. And we call that pressure difference across the hole a driving force often. And so when we think about air movement in our houses, you can think of this balloon as a house, and you can think of the rubber membrane of that balloon as the building thermal envelope of that house. So if I have this continuity of this building thermal envelope or rubber membrane, you can see that I have equalized the pressure inside the balloon and outside the balloon. However, if I untie the string of the balloon, I create a hole or a pathway, and I create an unbalanced pressure dynamic here. So we're going to have greater pressure outside the balloon than we have inside the balloon, and we're going to push air out of the hole. So ultimately, again, I need some type of hole and some type of driving force to push air through the hole there. So we have lots of holes in our building envelope, and the code is telling us to seal up those holes. And this is one example where it's telling us how to seal the hole at the rim joist and sill plate foundation connection. And it goes through in this table and gives us a checklist of all these areas that we can seal up our houses. And if we follow this checklist in the code, we should be able to achieve a house that achieves 3 air changes per hour as required in our climate zone here in Colorado on the Front Range of 3 air changes per hour. Now you can see in the 2021 IECC, all of these components listed on the left-hand side here of the table and on this slide are things that have been changed or updated in this table for the 2021 IECC to give us even a better chance of achieving that air tightness that's required by the code. Now, when we're trying to meet this requirement, we have to test the house. We have to do what's called a blower door test of the house in order to quantify if we've made that 3 air change per hour requirement or not. And that blower door test works on a pretty simple principle. It works on the principle of air in equals air out, or air out equals air in. So the building thermal envelope defines a specific amount or volume of air inside that house. And we measure it in cubic feet per minute of air moving in and out of that house. And a cubic foot per minute, or a cubic foot of air, is about the size of 4 basketballs. So you can think about when a cubic foot of air leaves the house, that's 4 basketballs of air leaving the house. And that means 4 basketballs of air have to come back in the house. So when we set up a blower door in the house, we depressurize the house. We suck air out of the house. And if you look at the picture on the top right side here, the more air that leaves the house, that means I have a lot of holes in the building envelope, because that same quantity of air leaving the house has to be replaced by the same quantity of air coming back in the house. In the same way, if I have a tighter house, that means less air, less cubic feet of air, fewer basketballs are going to go out of the house. That means fewer basketballs or fewer quantity of cubic feet per air are going to be coming back in through the holes, because I don't have as many holes. But I do with the blower door, I have created that dynamic where I have a pressure difference across the hole. In this case, I have a negative pressure inside the house and a positive pressure outside the house. And I have a hole. So I'm able to move air through those holes. And under these test conditions, I'm able to determine how airtight a house is. So ultimately, what does this pressure mean? Air pressure is created in a variety of ways in our houses, kind of continuously. throughout the life of that house, every day, every month, the pressure dynamic is changing. So we have these things, just wind blowing against our house that create a pressure difference. We have this stack effect, or when air warms and moves up and then out of our houses, it causes air to come back in. And then we could put in our houses mechanical systems like HVAC systems with ductwork, or just a fan in the bathroom that can create a pressure difference across the building thermal envelope. So those are the forces that are impacting that boundary condition between conditioned space and unconditioned space, and creating positive, negative pressures in our houses. When we're measuring those pressures, we always are measuring across a boundary. So we always want to speak with this language that says we're measuring the house pressure in relationship, or with regards to the outside. We're measuring the duct pressure in relationship to inside the house. So the duct pressure inside the duct in relationship to outside the duct here. And when we're measuring it, we're using this unit, this metric unit of pascals, which is a weight measurement ultimately here. And that Pascal measurement is a small but really powerful unit of measurement. It only takes a very small amount of negative pressure to backdraft an atmospherically vented water heater. To put that pressure into a frame of reference, I guess, we can think of another way of measuring pressure, or atmospheric pressure, and that would be with a water column here. So a water column, 1 inch of water column is equivalent to about 250 pascals of pressure, and 4 inches to about 1,000 pascals of pressure. 1 pascal, you can also think of it as the weight of a Post-it note pushing down on your hand, is equivalent to about 1 pascal of pressure. So again, this very small negative pressure of 3 to 5 pascals of pressure can backdraft an atmospherically vented water heater. So it's just a very small amount of negative pressure in that case. One last way to kind of describe a pascal, there's about 250,000 pascals of pressure inside of a car tire that's at 35 PSI there. So the next question I wanted to ask people is, can a house be too tight? Because we're measuring it with a blower door. This question comes up a lot, and we kind of need to understand what the code is trying to do.
All right, Robbie, I've launched the poll. Give it a little bit more time here. We've got about 50% participation so far. All right, I'm going to go ahead and end the polling.
Great. So the answers that we got back indicate that about 63% say no and 37% say yes. And if you're keeping score at all, the answer to the question would be, if I can get back here, would be no. We can't build our house too tight. The reality is that we're asking the wrong question. Because ultimately we want to gain that control and that predictability of airflow through our houses, the only way that we can really do that is by building our houses tight. I don't have control of the pressures or the driving forces, the wind, for example, or the stack effect, air warming and rising out of my house. I don't really have control over that. What I do have control over is the amount of holes that are in that building thermal envelope that are going to cause air to move from inside to outside, or from outside to inside. So what is the real question that we ultimately should be asking? The real question is, can our houses be underventilated? And the resounding answer to that is yes, they can be underventilated. So from a building science perspective, we want to build as tight as we can, and we want to ventilate correctly for the house and for the occupants. And now the code is asking us to ensure that that's happening by actually testing and quantifying and making sure that we're meeting what the requirements of the code are for building tight and ventilating correctly here. So we have these mandatory requirements, And those mandatory requirements, again, are to build tight and ventilate right here. So from a testing requirement perspective, when we're doing a blower door test, the 2021 IECC has actually created some confusion in my mind here. They've done that with this first text that is written in the new code book, the 2021, and it says that the building dwelling unit shall be tested, which makes sense. That's consistent through, since at least the 2012 IECC, but now it says the maximum air leakage rate for any building dwelling shall not exceed 5 air changes per hour. They also added a new metric for measurement, the CFM per square foot of dwelling enclosure area there. And what they're ultimately saying here is that in the sections R405, the building performance section, and section R406, the energy rating index section, they're saying that you can't trade off house tightness for more R value someplace else. So when you're talking about a trade-off, you're talking about the ability to put something less somewhere in the building and put something more somewhere else in order to trade off performance, but ultimately keep a balance point of the energy use that's required by code, or the energy efficiency that's required by the code there. So this section is actually what we call a backstop for the building performance path and the ERI pathway in code to say that you can't trade off beyond 5 air changes. Where it's located in the code, I think, creates confusion, and that they aren't more specific that this is intended for those 2 pathways is also confusing here. Now, the next section of the code language is also, I believe, in the wrong place. And we're actually going to put in an errata proposal to change this around so that it reads better and people can understand how it's intended to be used. But this exception is actually intended for the 3 and 5 air change requirements, or for any, that base requirement that is required in all climate zones here. And what it says is that if you have you're allowed to use a 0.30 CFM per square foot of dwelling enclosure area in any climate zone if you're looking at an attached single family or multifamily building, or a single family home that's 1,500 square feet or smaller. And the reason that this new metric has been put in place is because the air change per hour metric is a volumetric measurement. And the larger the house is, the more volume of air is in that house, the easier it is to achieve 3 or 5 air changes as required by the code. The smaller the unit, the harder it is to achieve that if you're looking at a 3 or 5 air change per hour metric. So this 0.3 CFM per square foot of dwelling enclosure area is measuring the air that comes through specific holes in that building envelope. So it's a more accurate way of defining air leakage, and it works better, especially for small units, but it works fine and equally as well for larger units. So I think over time, we will move to this metric, but this is the first introduction of a better metric for use for quantifying the air leakage of homes in the IECC, and it's happening here in this section here. Now, the last place that mentions air tightness in the code is talking about air leakage from a perspective of the prescriptive sections of the code that have to meet at least a 3 or a 5 air change requirement, regardless of, dependent on the climate zone that you're actually in. So again, what we just talked about, this CFM per square foot exception, should actually go after this part of the code here, there. So, but regardless of that, we know that our houses in climate zone 5, for example, can't leak, regardless of the pathway that you're using, can't leak more than 5 air changes per hour, and in most cases are going to be tighter than 3 air changes per hour there. And we use a blower door to answer that question of how airtight did the house actually get, and does it meet the ultimate requirement of the code? We know how much air leakage is happening under natural conditions, potentially, if we want to. We can also see how successful our air leakage measures have been, how well we've done at tightening up the house, how much control and predictability we've gained of the air that's flowing in and out of our houses that might be creating condensation inside our building assemblies there, because we've done a better job of stopping infiltration and exfiltration. And then it can also help us assess this duct leakage to outdoor test that we're going to show you here in a minute. So the other thing that the code is asking us to do is to report these findings that we've gotten. And this report actually needs to be submitted before the certificate of occupancy is released. So we can use this type of report. This is just an example of reporting. You'll see a variety of different reports that come to you. But in this example, this one report reports the air leakage rate in the house. It reports the duct leakage rate in the house, and it reports the mechanical ventilation rate in the house. And all of these tests, there is a requirement in the specific sections of the code. I'm only showing you the air leakage section, but in all the sections, it's telling us that we have to report to the code official the findings of these tests before the certificate of occupancy is ultimately released. These are part of the compliance report packages for the confirmed house. That means the house that is finished its inspection process and is ready to get its certificate of occupancy there. Okay, so going back real quick to this difference between air leakage and ventilation. So we've tested for air leakage, but do we really know what air leakage is? Air leakage is this infiltration or exfiltration. So it's really this unintentional, uncontrolled, or accidental movement of air in or out of the house. It really impacts the energy efficiency, the comfort, safety, and durability of our houses. And it is a specific infiltration load that is accounted for in our HVAC design calculations that we do. Now, ventilation, which we'll get to in a little bit, is more of an intentional, controlled, and predictable process of supplying or removing air out of our houses. We've put that ventilation air at a specific rate, so I know exactly how many cubic feet of air are coming in and out of our houses. And we put it at a specific schedule, so I know how often that ventilation fan is running in my house. It also creates a ventilation load that is separate from the infiltration, exfiltration, or air leakage load in our houses. And it also needs to be incorporated into the design calculation. Now, ventilation, again, from a control and predictability perspective, is giving us greater control of the fresh air that we're providing for the occupants of that house, and also control and predictability of the moisture inside of our houses that could create durability or potentially safety issues and indoor air quality issues with mold and whatnot there. So this air leakage equation, we're testing our houses, and there are a couple of different ways of doing tests, but it doesn't necessarily mean that we're allowed to do these different tests in our houses. For a single family detached home, that is what's described really in our houses. But you can do a single family detached test on a multifamily house as well. It's just we're not quite as certain where all the air that's leaving through the blower door is coming from. It might be coming from an attached unit, or it might be coming from the outside. When we look at multifamily buildings, you can see that this, what we call an adiabatic wall, means that there's not necessarily a temperature difference from unit to unit, but it doesn't necessarily mean that those units aren't connected from an air leakage perspective. This type of area separation wall is called a shaft liner wall. It tends not to have a lot of connection from unit to unit, but this gap is open up to the ventilated attic. So we have a lot of connection to the outside and potentially to the outside from the front and back of the units. Other types of attached housing, however, might be connected from unit to unit. So this CFM per square foot of enclosure area helps us with what's called compartmentalization, as well as ensuring that we're able to measure the air leakage from indoors to directly outdoors. We're also able to measure the leakage from unit to unit. This gives us the ability to deal with the energy efficiency issue, but also deal with the secondary issue of odors or smoke or other things that might connect or might pass from unit to unit there. So this test is now allowed by the code. You can use the CFM per square foot of unit enclosure area when you're doing code compliance testing there. But this next one, which is called a guarded test, is not actually called out for being allowed in the code. What a guarded test does is you set up, you're wanting to get the results for the red blower door in the center there. But in order to test just the leakage that's happening from indoors to outdoors, I can set up blower doors in the adjacent units so that when I depressurize all 5 units at once, I'm taking away the leakage from unit to unit and only quantifying the leakage that's happening directly to the outdoors. Now, this test has a couple downsides. The first downside is that it takes 5 blower doors to do the job that 1 blower door could do. The next downside is that it takes a technician to man each of the blower doors there, and so it becomes a very expensive process there. However, if you are coming across units that have a lot of leakage from unit to unit, and you're going to require them to meet an air change per hour metric instead of a CFM per square foot of enclosure area metric, you might be asked by folks that do blower door testing, can we do a guarded test? Will your jurisdiction allow that? So I just wanted to bring it up, because, especially for those code officials that are on with us today, because you might be asked about this guarded testing. You want to know a little bit about what it's about. The other type of testing that you might be asked about is, can I test the whole building envelope instead of a specific unit when we're talking about multifamily building? And if I can connect all of these units together to a common stairwell and hallway, and then ultimately make sure that this unit that's farthest away from the blower door can see the blower door, that the air can travel freely through the blower door, then I could set up a number of blower doors in that opening and potentially depressurize the entirety of the building thermal envelope, so that red dashed line there, and get you a number for the air tightness of the entirety of that building. And this also might be something that somebody might ask, will you allow that in your specific jurisdiction? Will you allow us to test the entirety of the building envelope instead of just unit A, B, and C separately there? So just as a reminder, you can do a variety of different types of blower door tests, single unit or single homes, compartmentalization, whole building testing, or this guarded testing there as well. Okay, so we're going to move on to the next type of testing that's called out in the code. This is called duct testing. Now, when we're doing duct testing, we need to define what we're testing, and it's the entirety of the HVAC system that has a duct. So we want to make sure you understand that it includes the air handler, filter boxes, and if you happen to allow building cavities, it would include those building cavities as well if they're pressurized duct systems. But the reality is that the code is telling us we can't use pressurized building cavities as ductwork. So here's some examples in the past where building cavities were used as ducts. And you can see that this return is not only supplying air from this room, but there's a quantity of air that's coming from an attic on a hot summer day that is extremely hot. So you're taking extremely hot air back through this building cavity, ultimately to the return side of this HVAC system, and probably across a cold HVAC coil. Very impractical, inefficient, and you also are have questionable indoor air quality because that air is potentially bringing in pollutants, hot air, but also fiberglass fibers or other things like that, and you're distributing it around the house ultimately. So this is a requirement that's in the IECC that says you're not allowed to use building cavities. When we test these systems, they're very difficult to make airtight. And when we test these systems, we follow this process when we're doing a duct leakage test. The first thing is to block off all intentional openings that are in that HVAC system. So all the supplies and returns in the house. We need to open a window to equalize the pressure inside the house in relationship to outside the house when we're doing total leakage. We set up our duct testing device. In this case, it's called a duct blaster from this manufacturer. We have to put a pressure probe inside the duct in relationship to outside the duct so I can measure the pressure inside that duct work in relationship to outside the duct work. Then I pressurize, or I potentially could depressurize as well. You're allowed to do either or, but you want to make sure you know which direction your fan is blowing or sucking. And so I'm pressurizing the duct to a common pressure of 25 pascals in that duct. That's my common pressure, consistent pressure, so that everybody across the country is testing in the same way when we test for duct leakage. So in this case, you can see on the B channel side or the modes channel side of this gauge, I haven't actually reached 25 pascals of pressure, but the flow, this is a smart gauge, so the flow is able to read the pressure as if I were at 25 pascals of pressure and give me a flow reading of 32 CFM of duct leakage in this particular scenario here. Now, the duct leakage requirement is called out specifically in the code. It says, if I'm going to test at a rough stage of construction, I have to meet 4 CFM per 100 square feet of conditioned floor area. So if I have a 2,000 square foot house, my duct system can't leak more than 80 CFM at 25 pascals of pressure, that consistent testing methodology that everybody's using. So the test I showed you before means that this house was leaking 32 CFM. It's going to pass the requirement of the code there. Now I'm given the ability to test with the air handler present and with the air handler not present. If it's not present, it's a little tighter, that system that I'm looking for. And I can also test after construction versus at a rough stage of construction. And I just wanted to point out that it makes a much more sense to test at a rough stage of construction because the ducts can actually be fixed at that stage in an economical manner if they don't meet these testing requirements there. Then when the air handler, the other thing that is required now in the 2021 IECC is that regardless of the location of the ducts have to be tested. And if the ducts and all the air handler equipment is located inside the building thermal envelope, you have a much leakier system that you can comply with. So in this case, 8 CFM per square foot of conditioned floor area. So this is a pretty big change from the codes before the 2021. In the previous codes, it said, if there is any portion of duct or air handler outside the building envelope, I am forced to test the system. Now it says, regardless of where the ducts are, you have to test. And if all the ducts are inside the building, you have a little bit of more leeway. You can have a little bit more leaky system. if you want. It doesn't mean that that system's going to perform as well. It just says I don't have to meet as tight a target for my duct system there. The next thing I wanted to talk about with regards to ducts is this duct leakage to outside testing. Duct leakage to outside testing requires the use of a blower door and a duct tester working simultaneously in our house. And it's only, this type of testing is not specifically called out as a requirement in the code, but when you're using the building performance path, that used to be called the simulated performance path in the code, but in the 2021 cycle, it's now called the building performance path or the energy rating index pathway. If you want to take advantage of duct leakage, having a tight duct system, and trade it off for less R value someplace else, you have to be able to quantify how much leakage is happening directly to the outdoors, because that is the energy penalty. If the duct leakage is leaking inside the building envelope, then it's not considered an energy penalty. It might not be as comfortable in that house, but it's not a true energy penalty here. So when I do a duct leakage to outside test, it's a little bit more complicated for a couple of reasons. But I start out by blocking off the supplies and returns, known openings like I did before. Then I need to pressurize the building itself. So I use the blower door to pressurize the building to that 25 pascals of pressure. By doing that and leaving the duct blaster open to the house, I've also pressurized the duct to 25 pascals of pressure. So I have equalized the pressure inside the duct system and outside the duct system that's located inside the house. So you can see here, the pressure is equal. So if I have a hole in that duct system, remember I have to have a hole, but I also have to have a pressure difference across that hole for the air to flow out here. I've taken away that pressure difference. So the only leakage is outside to outside, like in this ventilated attic or this ventilated crawl space. That's the measurement that I can now take here. So what I end up doing is I measure the pressure in the duct, and it's telling me that it's a negative pressure because air is leaking outside my house, outside the building thermal envelope through the duct system, but it's outside the building envelope. What my goal is to next is to zero out this pressure. So I turn on my duct blaster in this case, and I zero out this pressure, and it tells me the CFM of air that it takes to zero out that pressure. That tells me the CFM of air that is going out of this hole and this hole to the outside ventilated attic and ventilated crawl space. In this case, 72 CFM of air is leaking outside. Now, the lower that number is, potentially, the more I can trade off for something less somewhere else. So if my duct system is not leaking very much to the outdoors, then I'm getting better efficiency through my duct system, and I could potentially trade that off for less R value somewhere else. That's how trade-offs work. Okay, so it's time for another poll question. This poll question is, would you like to see a blower door and duct leakage test in the field? It kind of gives me an indication of how many people have actually seen this in the field, but we're also kind of wondering, would people want to go out in the field and see a demonstration of these tests?
We'll give it another couple seconds here. All right, and I'm going to end the polling. Okay. Do you see the results?
Yeah, so 83% would like to join us in the field at some point. So we should keep that in mind, Erica, for our next rounds as the weather gets nicer here. We might be able to do that.
Definitely.
Duct leakage location is another thing that's called out in the code. here, and there's some new definitions in the 2021. So I just wanted to bring that up. It could impact the test results, but remember, regardless of where the ducts are located, you have to test the ducts now. There's some other tests. There's some other tests that you can also do that aren't required by the code when you're talking about trying to understand the performance of an HVAC system. And ResNet, or the Residential Energy Services Network, is starting to give you some credit when you're quantifying the energy performance of the house if you do some of these tests as well. Okay, so we're going to spend the last of our time today talking about ventilation and ventilation testing here, the V in the HVAC. Remember, we need to build tight and ventilate right. So the code is telling us that we have to ventilate our houses if our houses meet the air leakage requirement of the code. And the air leakage requirement is a mandatory requirement. So we can't have a house that leaks more than 5 air changes per hour in any climate zone. But in most of the colder climate zones, it's really 3 air changes per hour. So this requirement in the IECC takes us over to the IRC, where it says first it says in the IECC, mechanical ventilation shall be provided. And then we go over to the IRC and it says we can use supply side, exhaust side, or balanced ventilation strategies. We have to have some type of mechanical or some type of control, and that control has to have the ability for the homeowner to override it if they want to. Even if we don't want them to, they have to have that ability there. These systems have to run at a continuous rate, or if they follow a specific schedule, they could run intermittently as well. So you're basically getting the same volume of air running through the house, but it's running at higher quantities if it's running at intermittently, and lower quantities if it's running continuously, but the same exchange rate is happening over a 24-hour period of time. Remember, the ventilation, allowable ventilation styles, or you can use a positive pressure, a supply side system. You can use a negative pressure system or an exhaust side system, or you can use a balanced ventilation system like an ERV or an HRV. That would be an equal pressure system in our houses. Regardless of the system you choose, you have to size the ventilation rate according to the requirements of the code. The code says you can use this table and size a 4 to 5 bedroom house that's 1,500 to 3,000 square feet. It would require 75 CFM of ventilation running continuously, or slightly more than that if you're going to run it intermittently. And it gives you an equation for how to come up with that intermittent CFM rate. It also gives you the ability to use this formula instead of the table. Most consultants anyway would err on using the formula instead of the table, because it better right sizes the ventilation that's required here. So if I do this calculation for the small side of the equation of this house, you'll see that its requirement is 52 CFM instead of 75 CFM. And there is a fair amount of concern out there from different building scientists that we might be over ventilating our houses. So you'll see that a lot of groups are using the formula rather than the chart or table to determine the ventilation rate. Now, the ventilation rate, there is an exception here that says that the ventilation rate may be reduced by 30%, provided that both of these things that are listed below occur in that house. So you'll need to take this into account as well when you're determining the ventilation rate. And it would be something that would be good to look for in your plan documents when you're doing your plan review for permitting, to understand what ventilation rate is, how it's been sized for that particular house, so that when you get the compliance document or report for the certificate of occupancy, you know that if it's going to pass or not there. So that's whole house controlled mechanical ventilation. We also need to think about spot or local ventilation. That's ventilation that occurs in kitchens, bathrooms, and laundries. in order to get moisture up and out of the house as soon as it's being produced in that house. Now, this exhaust rate is talked about in the code as well. It does take you to the IRC as well to look for those ventilations rate. And it says that rooms containing bathtubs, showers, spas, or other fixtures need to be mechanically ventilated here. And in another section, it talks about kitchens as well. Now, the kitchen ventilation rate is 100 CFM intermittently and 25 CFM continuous. Bathroom fans are 50 CFM intermittent and 20 CFM continuous. And as you can get an indication from the pictures below, this ventilation rate is really solely dependent on if it gets achieved by how well the ducts are actually installed in that house. If the ducts are tied in knots or have big 180 elbows in them, sometimes even a smooth 90 elbow can impact the ventilation rate as well. Now, the pictures on the right side of this slide come from Panasonic's guide for how to install that ductwork so that it actually works in conjunction with their fans. So you can get an idea that we want minimal elbows in that duct, smooth duct, and good terminations where the air is leaving the house there. And with regards to the air leaving the house, that's also a requirement there that this exhaust system gets sealed up well. So we should be looking for mastic or duct tape, or not really duct tape, but air sealing tapes on these duct systems, as well as that the dampers inside of these fans aren't impinged by screws or other things that you can see in the lower picture on the right here. And we need to see that those are sealed just like any other duct there is being sealed. All of this duct is also required in the code to be ducted all the way to the outdoors. It can't just be left hanging in a crawl space or an attic or someplace like that. And then what's new ultimately in the 2021 IECC is that mechanical ventilation systems shall be tested and verified to provide the minimum ventilation flow rates required by section R402.4.1.2. So this is new language to the 2021 IECC. Before we had to meet those ventilation rates, but as my mentor used to say, you get what you inspect, not what you expect. So we had no way of knowing for sure that they were meeting that ventilation rate. And if those pictures before tell us anything, most likely when the ducts are tied in a knot, we're not going to meet that ventilation rate. So the testing needs to be performed according to manufacturer instructions, and you have to provide a report. It can be done by third parties, or it can be done by the code official themselves there. There is an exception to this with regards to kitchen hoods. If you have a kitchen hood, because it turns out that kitchen hoods are difficult to test, is being vented with a 6-inch or larger duct and has one or less 90-degree elbow in it, then you are not required to test that kitchen range hood here. Now, when we're testing balanced ventilation systems, these are ERVs or HRVs. Luckily, a lot of those systems come with pressure ports built into the system, so you can balance the system and measure the flow rate there. Otherwise, you need to use a device like this on the right-hand side here, some type of pressure probe, and measure the pressure inside the duct as it's passing through and passing by that probe or that pitot tube. Ventilation from a supply side ventilation scenario also means that you need to generally use a static pressure port, although sometimes these inline fans come with means of measuring the pressure and also adjusting the flow rate of the fan as well. And I think over time, we're going to start seeing these type of pressure measurement ports being installed with these systems now that this requirement is there, so that you can actually balance or in essence commission the ventilation flow as it comes. Now, exhaust ventilation systems, you can measure them as well, but a lot of these exhaust ventilation systems are really high quality bath fans, and they come with different means of measuring or determining the flow or adjusting the flow rate and the time run for those systems. And you generally use a flow hood to measure the flow through an exhaust ventilation system. Now, a flow hood uses this flow box. For example, it gives you the pressure that's going through this hole in the flow box here. And I can go over here and look at negative 3.7, 3.8, and the opening that is in my box. And in this case, I'm getting 85 CFM here. And just one other example here, I'm getting 14 CFM. So obviously a bath fan has to be able to push at least 50 CFM. So one of my tests passed and another of my tests failed. Most likely it's the installation of the ductwork that causes it to fail, which could also mean the dampers as well. So remember, with regards to kitchen hoods, they do need to be tested unless you have a duct that's at least a 6-inch duct or bigger, and it only has one bend in that ductwork, 190-degree bend in that ductwork. We actually probably should have talked about the quality of the ductwork as well. This type of flex duct should not be used on any of the ventilation systems there, unless you can ensure that it's pulled tight and made smooth, and that you have a smooth elbow in it as well. So to start concluding here, to understanding diagnostics, and again, it gives you that ability to get what you inspect, not what you expect from the system, so to definitely determine if they met the requirement of code or not. Our ultimate goal here is to gain control and predictability of the heat flow, airflow, moisture flow in our houses. So in order to do that, we need to build tight and ventilate right. And heat flow and moisture flow are so interlinked with airflow that if we know that we're getting the proper airflow through the house, we're going to have better heat flow and moisture flow control in that house as well. Remember that airflow is driven by holes and driving forces or pressure differences across that hole. So we have different techniques of measuring it for house leakage, duct leakage, and ventilation quantification or ventilation leakage as well. Now, what I believe the next frontier from an inspection perspective and diagnostic testing inspection that's going to be required by code is this requirement in the air barrier and insulation table to separate the house from the garage. We can actually do a test, a very simple test when we're running the blower door. We can measure the pressure difference between the house and the garage, and I can tell you if it's connected to the house or not. And because our garages, we store so many pollutants in that garage, like paint and gas, and we start our cars in our garages, and we get all that carbon monoxide in there. It's an interesting question. Should we actually be quantifying and know for sure that that garage is separated from the house from a health and safety perspective that the code is always kind of looking at as well? So that leads us to our last poll question. Do you think garage separation should be tested?
Give it another 5 seconds. All right.
So 82% say yes. Well, that's great. And maybe in this next code cycle, we can work on that together here. So to conclude, remember, air movement is driven by holes and driving forces. It's a fluid, just like water is a fluid, so it works on that same principle. We reviewed the different types of blower door testing and the requirements from the code. We reviewed the two types of duct leakage testing and the requirements there. And now remember, in the 2021 IECC, ventilation testing is a requirement. And then ultimately, as my mentor used to say, you get what you inspect, not what you expect. So thanks so much for spending some time with us today. Really appreciate it. If you have any questions or follow-up, I'm happy to stay on longer and have a discussion, or you're more than welcome to reach out to me, email or by phone, and take a look at our my Instagram account, because we're doing a deep dive into the energy code every week, releasing 10 more slides and working our way through the energy code there as well. So thanks a lot.
Great. Thank you, Robbie. If anyone has any questions, feel free to write them in the Q&A. It does look like we have a raised hand from Kendall Moore. I'm going to go ahead and unmute you, or allow you to talk, Kendall. If you want to go ahead and unmute yourself, you can ask Robbie any questions you have directly. I think we might have lost her.
Okay. Well, I must have just done an amazing job. There are no questions. So.
Yeah, exactly.